We propose a single-shot HDR imaging technique using a jointly learned diffractive optic and reconstruction network. Real-world scenes span a large dynamic range, and for this reason, HDR imaging is essential for a wide range of applications in uncontrolled environments, such as autonomous driving, robotics, and mobile photography. Existing burst methods are unsuitable for dynamic scenes due to ghosting artifacts. These artifacts can be removed in post, but the capturing and post-processing time is prohibitive for real-time applications. Alternative sensor designs that spatially multiplex multi-exposure captures suffer from reduced spatial resolution, and gradient cameras impose challenging reconstruction problems. Recently, deep learning has been used for HDR prediction from a single shot. However, these methods also fail to recover large dynamic ranges. Another single-shot approach uses a star filter on top of an existing lens system to encode saturated scene content into unsaturated regions. Although this allows for better prediction of high-intensity content, it leaves behind noticeable artifacts in the unsaturated regions. As such, HDR imaging for high-contrast dynamic scenes at real-time rates is an open challenge and an obstacle for robotic and automotive applications. We address this open problem by proposing a snapshot HDR imaging technique. Our method performs optical encoding using a learned diffractive optic and recovers the latent HDR image using a specialized reconstruction network. Both the optic and the network are optimized end-to-end using a fully differentiable image formation model, and inference runs at real-time frame rates. Even when initializing our method with a Dirac peak, the learned encoding optically multiplexes HDR regions into nearby unsaturated regions. A capture is shown here. We now explain our imaging pipeline. We first begin with an HDR scene. The scene is modulated by our DOE and focused onto the sensor. We simulate this using the point spread function of the DOE. The captured image is then fed into our reconstruction network. We first separate the optical encoding from the unsaturated regions using a residual splitting subnetwork. Next, a highlight reconstruction subnetwork uses the residual optical encoding to predict the saturated content. Finally, we combine the saturated and unsaturated predictions using a fusion subnetwork to produce the final HDR prediction. After training and fabrication, we replace our optical simulation with images captured from the hardware prototype. Our DOE's height map is parameterized using a Rank-1 decomposition. This allows for easier training and permits both global and local optical encoding patterns. Our technique outperforms existing single-shot approaches relying on manually encoded streaks or learned encodings. See several artifacts around the light fixtures highlighted here. Furthermore, HDR CNN fails to estimate high-intensity scene content, and glare HDR and deep optics both have reconstruction failures. Our method correctly recovers saturated scene content while avoiding leftover artifacts. We now present our HDR capture results. Note the encoding streaks in the sensor measurement. Here you see fine highlight regions recovered. Here is a large area light source embedded in a backlit sign. We accurately recover highlight regions around the sign. Here is another example where the high-intensity regions prohibit imaging the fine detail of the brick structure behind the sign. The proposed method recovers this fine background detail from a single shot, as shown here. Our method excels at recovering small, bright sources, such as the halogen and incandescent light sources, shown here. Our technique reconstructs dynamic HDR scenes without the artifacts introduced by traditional burst methods. This scene consists of a swinging pendulum with lights. And despite the scene motion, we accurately recover highlight regions. We proposed a snapshot HDR imaging technique using a jointly learned diffractive optic and reconstruction network. Our technique handles dynamic scenes and outperforms recent single-shot methods.